Hi there, Professor Barber here. This lesson is titled Complex Zeros and the Fundamental Theorem of Algebra. In the set of real numbers, an nth degree polynomial has at most n real zeros. Let me explain what that means. If you are looking at a quadratic function, it can have two intercepts through the x-axis, but guess what? It could also have only one, and it could also have none. So in the real number system, you could have at most 2, but you can still have less than 2. In the complex number system, an nth degree polynomial has exactly n zeros, counting multiplicities, and so can be factored into exactly n linear factors. This is a consequence of the fundamental theorem of algebra. The learning objectives for this lesson are: 1. Know and be able to apply the fundamental theorem of algebra. 2. Know and be able to apply the complete factorization theorem. 3. Be able to compute complex zeros of a polynomial function. And 4. Be able to factor polynomials into linear and irreducible quadratic factors. Roman numeral 1, the fundamental theorem of algebra and the complete factorization theorem. The fundamental theorem of algebra states, every polynomial p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus plus a sub 1x plus a sub naught, where n is equal to or greater than 1, a sub n does not equal 0, with complex coefficients has at least one complex zero. Before we continue, note that complex coefficients does not necessarily mean imaginary numbers. A real number is a complex number with the imaginary part 0. Keep that in mind when you're looking at least one complex zero. Again, the complex zero does not necessarily mean you have to have an imaginary part. Every real number is a complex number with the imaginary part 0. And the complete factorization theorem. If p of x is a polynomial of degree equal to or greater than 1, then there exist complex numbers a, comma, c sub 1, comma, c sub 2, all the way to c sub n with a not equal to 0 such that p of x equals a times the factors of x minus c1 times x minus c2 times x minus c sub n. What this is telling you is that if you have a second degree polynomial, it will factor to 2 linear factors. If you have a 10th degree polynomial, it will factor to 10 linear factors. They don't necessarily have to be distinct. For example, you could have multiplicities of greater than 1, but you will have 10 linear factors for a polynomial of degree 10. Suppose the zeros of the 4th degree polynomial p are 5, -2, and 14i. Write the complete factorization of p. The issue here is we are told that this is a 4th degree polynomial, but are given only 3 zeros. So we must remember the complex conjugate theorem, which says that if 14i is a 0, then so is -14i. Now let's set this up. P of x, we're going to have 4 zeros, so 4 factors, x minus, that's 1, x minus, that's 2, x minus, that's 3, and x minus, that's 4. Let's put in the zeros. 5, -2, 14i, and the one that you had to remember to get but was not given to you in the problem is -14i. Ooh, that's messy looking. Let's clean that up. So we'll have that p of x is equal to x minus 5 times x plus 2 times x minus 14i times x plus 14i. Roman numeral 2, zeros and their multiplicities. If the factor x minus c appears k times in a complete factorization of the polynomial p of x, then we say that c is a zero of multiplicity k. Suppose the zeros of p are 5 with multiplicity 1, -3 with multiplicity 2, and 4 minus 1. Write the complete factorization of p. What we must remember is that if you have a complex root, then its complex conjugate is also a 0. So let's just go ahead and write if 4 minus I is a 0, then so is 4 plus I. Now let's set this up. We'll make it polynomial with respect to x. We have a 0 at 5, so x minus 5 of multiplicity 1. We have a 0 of -3, so x minus -3 of multiplicity 2. And the tricky thing is the complex roots. If x minus 4 minus I is a 0, then so is x minus 4 plus I. Let's clean this up. We'll have that the polynomial p of x completely factored is x minus 5 times x plus 3 squared. And then distributing the negative, we'll have x minus 4 plus I and x minus 4 minus I. And that's the complete factorization. Roman numeral 3, complex zeros occur in conjugate pairs. The conjugate zeros theorem states, if a polynomial p has real coefficients and if the complex number z is a 0 of p, then its complex conjugate, denoted z with a bar over it, is also a 0 of p. Roman numeral 4, linear and quadratic factors. A quadratic polynomial with no real zeros is said to be irreducible over the real numbers. Every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors with real coefficients. Given that for the function f of x equals x to the fourth plus 5x cubed plus 10x squared plus 16x minus 32 have a real 0 of x equals 1 and x equals -4. So we're given 2 of the 4 possible zeros. Factor completely to express as a product of linear factors. There are several approaches we can take, but what I'd like to do is reduce down the powers using synthetic division. So let's list the coefficients of the dividend, which would be 1, 5, 10, 16, and -32, and pick either of the zeros. I'm going to pick 1 just because that's the first one that appears, and we're going to perform synthetic division. So bring down the 1. 1 times 1 is 1. 5 plus 1 is 6. 6 times 1 is 6. 10 plus 6 is 16. 16 times 1 is 16. 16 plus 16 is 32. 32 times 1 is positive 32. And you know what? It confirms that x equals 1 is a 0 because we got a remainder of 0. So we took care of one of the zeros. Let's just continue to factor down. And so this time I'm going to divide the remaining, which was the quotient, but now the dividend, with -4. So I'll just draw another synthetic division, L under it, and put -4 as my divisor. 1 comes down. 1 times -4 is -4. Adding in the column, 6 plus -4 is positive 2. 2 times -4 is -8. add 16 and negative 8 together, we get a positive 8. 8 times negative 4 is negative 32. And yes, we got another remainder of 0. So let's expand this out. What we have is that the polynomial x to the 4th plus 5x cubed plus 10x squared plus 16x minus 32 is equal to x minus 1. That's what we used as the first divisor. X plus 4. That's what we used as the second divisor. And what remains now will be 1x squared plus 2x plus 8. So we have reduced or simplified this polynomial to 2 linear factors and 1 irreducible quadratic. What we have to do now is reduce that irreducible in the complex number system. So let's look at the x squared plus 2x plus 8, and we're going to set that equal to 0 and use the quadratic formula. So we'll use the quadratic formula, which you have committed to memory, which states that x is equal to the negative of b plus or minus the square root of the b coefficient squared minus 4 times a times c, all divided by 2 times a. Let's replace those variables with the numbers. So we're going to have the negative of b was 2 plus or minus the square root of b, which is 2 squared, minus 4 times a is 1, times c is 8, and all of this is divided by 2 times a, which is 1. The rest is essentially arithmetic, so we can write this as negative 2 plus or minus 4 minus 32 is negative 28 divided by 2. So we need to simplify that negative 28. I'll move on up here and I'll get negative 2 plus or minus, and I'm going to put in a lot of steps you may not need, okay? I'm going to write this as, I can factor out the negative 1, so that's 1, and factor the 28 into the product of 7 times 4, divide that by 2. So I got negative 2 plus or minus I times, the square root of 4 is 2, so I'll just write 2 instead of the square root of 4. Times the square root of 7, all divided by 2. And we can do one more simplification, and that is factor out or cancel all the common 2's. And so we get negative 1 plus or minus I square root of 7. This means you've got 2 zeros. Those are x equals negative 1 plus I times the square root of 7, and x equals negative 1 minus I times the square root of 7. Now, in the previous factorization, we have p of x equals the linear factors x minus 1 times x plus 4 and the irreducible quadratic of x squared plus 2x plus 8. We just used a quadratic formula and found the 2 complex solutions for the x squared plus 2x plus 8. They were x equals negative 1 plus I square root of 7 and x equals negative 1 minus I times the square root of 7. Let's put those as linear factors in the place of the irreducible quadratic. So what would that look like? Well, we're going to have the x minus 1. That's not going away. X plus 4. And now let's just write x minus and x minus, and we're going to use the factors that we got, the solutions. And so the solutions were negative 1 plus I times the square root of 7, negative 1 minus I times the square root of 7. And let's just distribute that minus and we'll be done. So we've got p of x equals x minus 1 times x plus 4, and then distributing that negative, we'll have x, negative and negative is positive 1. Negative and positive would be minus I times the square root of 7. And we have x minus negative is plus 1. And then minus minus would be plus I times the square root of 7. Let's note you have 4 linear factors to go with the power of 4 or degree 4 polynomial. Consider the polynomial p of x equals x to the 4th minus 16. Part A, factor p into a product of linear and irreducible quadratic factors with real coefficients. Well, let's begin with what we can see. We've got that p of x is equal to x to the 4th minus 16. We could actually rewrite this as x squared minus 4 squared. My reason for doing this is so that we can see a difference of squares. And with that in mind, we can then have x squared minus 4 times x squared plus 4. Now, the x squared minus 4 actually still factors over the reals, and so we can further expand the x squared minus 4 to x minus 2 times x plus 2, but the x squared plus 4 is not reducible in the real number system, so we'll call this an irreducible quadratic. Part B, factor p into a product of linear factors with complex coefficients. So let's borrow the work we already did in Part A. We got it expanded to p of x equals x minus 2 times x plus 2, and then we had x squared plus 4. Now, if you can see how to factor this straightforward, that's okay, but if not, let's just go to the side, okay? I can look at x squared plus 4 equals 0. That tells me x squared equals negative 4, and when we solve for it, we get x equals plus or minus the square root of negative 4, which is plus or minus 2i. The square root of negative 1 is I, and the square root of 4 is 2. So we can expand this into a product of 4 linear factors to go with the degree 4, and write this as x minus 2 times x plus 2, x minus 2i times x plus 2i.